Hello and welcome to this applications webinar. This will be a webinar about PAHs in water with the SCION instruments 8300 and 8500 GC, combined with the 8700 MS single quad. My name is Lieke Roelse and I'm an application scientist in the applications department in Goes. PAHs in water. The first thing we're going to talk about is what are PAHs? Here you can see an example of a PAH I found in MS Workstation with our NIST library search tool. Then we're going to talk about the instrumentation. So here you can see the inside of our MS. The compounds first go to the transfer line, then to the source, then to the quad 0, the quad 1, and then to the detector. Then we're going to talk about the experimental side. The sample preparation, we did sample preparation with liquid-liquid extraction, the results, and the conclusion. So what are PAHs? PAH stands for Polycyclic Aromatic Hydrocarbons. They fall under the class of semi-volatile organic compounds, or SVOCs. PAHs are released into the environment by both human activity and natural processes, such as forest fires and volcanoes. PAHs are released by the burning of coal, wood, and other solid forms of fuel, as well as being present in vehicle emissions and cigarette smoke. PAHs are harmful to human health and therefore their presence within the environment requires monitoring. Human exposure to PAH can come from a number of sources, including but not limited to contaminated soil, drinking water, and food that has been smoked or cooked using methods such as char grilling. PAHs can come from several sources, such as pesticides, oil-based products, and fire retardants. Instrumentation. Either the 8300 or 8500 SCION instruments GC can be used, with the 8700 single quad mass spectrometer. We used a splitless injector with a tapered quartz liner. The tapered liner focuses the sample on the entrance of the column, which is perfect for trace level analysis. Here you can also see the part number of the liner if you want to order it. Helium gas is the chosen carrier gas at 1.5 ml per minute. In this method we use a pressure pulse splitless injection. The pressure pulse is on at 25 psi for 0.75 minutes and the splitless time is set at 1 minute. Using a pressure pulse is only possible in constant flow mode. The pressure pulse increases the pressure for the set time during the initial analysis, resulting in more sample on the column and less sample loss in the injector. This increases the overall sensitivity. The pressure pulse is usually set between 25 and 40 psi, and for a shorter duration than the splitless time, typically between 0.25 minutes and 0.75 minutes. However, this can vary depending on the application. The SCION 5 MS column is used for this application, and this is a non-polar column ideal for the separation of PAH compounds. The oven program starts at 50 degrees and with a ramp of 10 degrees per minute it will go to 330 degrees. This is chosen to be sure that every PAH compound is out of the column at the end of the run. Putting the column to a high temperature at the end will make sure that the column will be clean before the next injection, known as burn off or baking. The 8700 SCION-MS is used in sim mode, giving a higher sensitivity and a lower noise. A single quantifier ion was used for each compound. This was chosen as the most abundant ion for each PAH. 2 qualifier ions were also used to help with identification of the compounds and prevent false positives. The transfer line and source temperature are chosen almost higher than the highest oven temperature to keep the compounds volatilized. The transfer line temperature is set at 325 degrees and the source at 350 degrees. A 5-minute delay collection time is set to avoid measuring the solvent peak, which will lead to faster contamination in the source. You can learn more about injectors, liners, and columns by clicking on the QR codes on the bottom. Experimental, a commercial available pH standard containing 16 pH compounds at 2000 microgram per ml was bought and used for this application. This was diluted and injected and the compounds were identified. Injecting a known standard is important because you will know for sure that the compounds you are interested in will be detected in the method with a known concentration. The linearity samples were prepared with dichloromethane at concentrations of beginning from 0.005 microgram per ml up to 1 microgram per ml. And then also 10 system precision samples were prepared at a concentration of 0.1 microgram per ml. An internal standard was also employed in this analysis to help improve the precision of the results. The peak area of the standard is divided by the peak area of the internal standard, giving a ratio. This ratio is used to calculate the results, making sure that any bad sample preparation or bad injection into the GC is resolved. The internal standard solution was prepared by adding 500 microliter of the internal standard into a 100 ml volumetric flask and making to volume with dichloromethane. 500 microliter of this working standard was added to each sample, giving the final internal standard concentration in all samples of 0.5 ppm. On the bottom here you can also scan these QR codes about QC best practice and internal standards. Sample preparation. For the validation of the method, spiked samples were made. The samples were spiked at the LOQ level, making sure that the method was working correctly. First, we made triplicate tap water samples. They were prepared by adding 100 ml of tap water to a Duran flask with 20 ml of dichloromethane. Also 500 microliter of the internal standard was added and the solution was stirred for 15 minutes. After a few minutes of stirring, two layers appeared. The top layer, 10 ml of dichloromethane, was extracted. The samples are now concentrated under nitrogen gas to a volume of 0.5 ml. This was injected in the GC. And for the recovery samples, 6 samples were prepared. This was done with the same sample preparation as the blank water samples. The only thing that changed was that instead of 20 ml of dichloromethane, 19 ml of dichloromethane was added to the water, plus 1 ml of the pH standard. The rest of the sample preparation was the same, and a sample was also injected into the GC. This was done to determine the LOQ that was required for the EPA regulations. Full scan. The first thing we did was injecting a high concentration of a known PAH standard with a full scan method. Each peak will be visible and very clear now, and if you click on a peak you will get a spectrum. The software can determine from this spectrum which compound it is. In this example you can see the compound fluorine. The spectrum is displayed under the selected peak and you can change this view to whatever preferences you like. The NIST library. The NIST library tool can be used to determine unknown compounds in your sample. If you click on the NIST icon in the software, the NIST library will open. The library will compare the found spectrum with known spectrums from compounds. And this will give a few options. Because the BOD standard has known compounds, we know for sure that for this example we have fluorine. The name, formula, CAS number, etc. is displayed in the NIST library search. Now you can make a spectrum list with each compound which you need for making a SIM method. To determine the correct quantifier and qualifier ions, you will choose the most abundant ions. In this case, ion 165 is the quantifier ion, and ions 166 and 163 are the qualifier ions. You can clearly see that those are the most abundant ions. In the software, the quantifier and qualifier ions are usually chosen when making a sim method, but you can always change this to your own preferences. The results. As I told you before, we will test in sim mode to improve sensitivity and lower the noise, because the MS will only search for specific ions. Using the quantifier and qualifier ions. This is an example mass spectra of fluorethane from a linearity sample, showing the quantifier ion the top plot and the qualifier ions the middle and bottom plots. The correlation values of the compounds demonstrate excellent linearity, with all results higher than 0.99. Typically, it is the testing laboratory decision to define the validation criteria, unless otherwise is stated in specific methods. For example, EPA 8270 requires a minimum correlation higher than 0.99, which is reached. The system precision values of all compounds demonstrate good repeatability, with all results lower than 4%. It is common industry practice to include RSD below 10%. The table shows some example recovery and precision values from the spiked LOQ samples, with recovery between 40 and 108% for all compounds. This was reached in the LOQ level. Spiked sample. Extracted blank has no PAH present. An overlay showing 2-bromonaphthalene from a spiked LOQ sample red and the water sample green. This shows that you have a clean GC and MS with no contamination. Spiked samples are important as they confirm the full working of the method, with good recoveries that will show you no ill effects from the techniques used in the sample preparation on the target analytes. Conclusion. So the conclusion is that the SCION instrument's GC-MS is the perfect solution for the PAHs in water analysis. We reached good method validation and achieved the LOQ with spiked samples. It is recommended to use quality control samples, for example, spiked samples at level 3, throughout the analytical run to monitor the status of the instrument over a lengthy runtime, around 20 samples. Thank you for listening to this webinar. If you have any questions, please don't hesitate to come in contact with SCION Instruments.